Welcome to the definitive guide to Norton's theorem. If you've ever felt overwhelmed by complex circuit analysis, this is the video for you. Here's a circuit. Voltage sources, loops, resistors everywhere. Your job, find the current through this load resistor RL. So you dive in. KVL, KCL, mesh analysis. You fill a page with algebra, solve a matrix, and finally, finding the answer. 5 milliamps. But then the inevitable happened. Your design requirement changes. What if RL is 10 kilo ohms? What if it's 100 ohms? You look at your work and realize you have to start all over again. Every time the load changes, you have to resolve the entire circuit. There has to be a smarter way. Enter Norton's theorem. It is the powerful twin, the dual of Thevenin's theorem. Here is the promise. Any linear circuit, no matter how messy, no matter how many components, can be reduced to just two things: a single current source, in parallel with a single resistor. We call this the Norton equivalent circuit. From the perspective of your load resistor, this simple model behaves exactly like the original monster circuit. It provides the exact same voltage and current. So instead of solving a complex system 5 times, you solve it once to find your Norton equivalent. Then, changing components is effortless. Now, I know what you're thinking. I just learned the Thevenin. Do I really need another theorem? Yes, because sometimes thinking in terms of current is much easier than thinking in terms of voltage. Norton's theorem is essentially source transformation applied to the entire circuit. If you understand the Thevenin, you're 90% of the way to understanding Norton. They are two sides of the same coin. Mastering both gives you the flexibility to choose the easiest path for any problem. Here is our plan for today. First, I'll explain the core concept. What are I Norton and R Norton? Then I'll show you the step-by-step algorithm to find them. Specifically, the short circuit method, which is the key difference from the Thevenin. We'll walk through a complete example, solving it from scratch. And finally, I'll show you the relationship between the Thevenin and Norton, so you can switch between them instantly. Ready to simplify your life? Let's get started. Let's go back to the black box concept. Imagine a box with two terminals sticking out. Inside, there's a complex linear circuit. You don't know what's inside and you don't care. Norton's theorem states that you can replace everything in that box with an ideal current source, which we call I Norton, connected in parallel with a resistor, R Norton. Why in parallel? Because current sources love parallel paths. If you look into those terminals, you cannot tell the difference. Connect a load and the current flow will be identical to the original circuit. Let's define our two new best friends. Parameter 1, I Norton, the Norton current. This is the current that flows through the terminals if you short them together. We call this the short circuit current, or ISC. I Norton equals ISC. This represents the maximum current the circuit can push. Parameter 2, R Norton, the Norton resistance. This is exactly the same as R Thevenin. It's the equivalent resistance characteristic of the circuit looking into the terminals when independent sources are dead. Because it's the same physical resistance, we often just call it equivalent resistance. R Norton equals R Thevenin. If you've watched my Thevenin video, you'll spot the pattern. Thevenin is voltage in series with resistance. Norton is current in parallel with resistance. In Thevenin, we look at the open circuit voltage. In Norton, we look at the short circuit current. They are mathematically related by Ohm's law. V Thevenin equal I Norton times R Norton. This means if you find one, you effectively have the other. But today, we are going to learn how to find the Norton equivalent directly, because for many parallel circuits, it is much faster. How do we find I Norton? The process is simple but specific. Step 1, identify the terminals, and B. Step 2, remove the load resistor. Step 3, connect a short circuit, a wire between terminals A and B. This is the magic step. By shorting the output, we force the current to show itself. Step 4, calculate the current flowing through that short wire. That current is I Norton. Let's try a mental example. Imagine a 10-volt source with two 5-ohm resistors in series. terminals are across the second resistor. Step 1, terminals A and B are across the bottom resistor. Step 2, remove any load. Step 3, short A to B. By placing a wire across the bottom resistor, we bypass it. Current takes the path of least resistance. All the current flows through the short and none through the 5 ohm resistor. Step 4, calc current. The circuit is now just the 10-volt source and the TOP 5 ohm resistor. I equals V over R equals 10 over 5 equals 2 amps. So I Norton is 2 amps. A crucial warning here. When you short the terminals, you might short out, bypass some components. Any resistor parallel to your short becomes irrelevant because current skips it to take the 0 ohm path of the wire. This simplifies the circuit massively, which is why the Norton method is often faster than finding the Thevenin voltage. You get to ignore parts of the circuit. Good news, finding R Norton is identical to finding R Thevenin. The procedure is the same. Step 1, remove load. Step 2, turn off kill all independent sources. Voltage sources become short circuits. Current sources become open circuits. Step 3, look into the terminals and find the equivalent resistance. Since we covered this extensively in the Thevenin video, I won't belabor it. R Norton is R Thevenin. Let's look at that previous circuit again. 10-volt source, 2 5-ohm resistors in series, terminals across bottom resistor. Find R Norton. Kill the source, 10V becomes a short wire. Now look from terminals A and B. We see the top 5-ohm resistor going to ground through the killed source and the bottom 5-ohm resistor. Wait, let's trace carefully. Terminals A and B are across the bottom resistor. Looking in from A, we go up to the top resistor, which goes to ground. Looking in from A, we go down. Actually, both resistors connected to ground. They are in parallel. R Norton equals 5 parallel 5, which is 5 ohms. So our Norton equivalent is a 2 amp current source in parallel with a 5 ohm resistor. Let's tackle a real problem. Same conceptual circuit as before, but with values that make us work. Voltage source Vs equals 24 volts. R1 series equals 3K. R2 shunt equals 6K. R3 series to output equals 2K. Load RL is connected at the end. Goal, find Norton equivalent. Step 1, remove RL. Step 2, short the terminals A and B with a wire. Step 3, find current through that wire. Look at the circuit. The short circuit connects the right side of R3 to ground, so R3 is now effectively in parallel with R2. No, wait, let's trace. Current leaves source goes through R1. At the node, it splits between R2 6K and R3 2K. Since R3 is connected to our short ground, it is indeed in parallel with R2. We need the current through R3, that's our short circuit current. Use current divider rule. Total resistance seen by source. R total equals R1 plus R2 parallel R3. R2 parallel R3 equals 6K multiplied by 2K divided by 8K equals 1.5K. Total R equals 3K plus 1.5K equals 4.5 kilo ohms. Total source current is equals 24 volts divided by 4.5K equals 5.33 milliamps. Now that current splits, we want the part going through R3. I short equals is multiplied by R2 over the sum of R2 and R3. I short equals 5.33 milliamps multiplied by 6K over 8K equals 5.33 milliamps multiplied by 0.75. I short equals 4 milliamps, so I Norton equals 4 milliamps. Now R Norton. Remove short. Kill source short 24V. Look in from N and B. We see R3 in series with the parallel combo of R1 and R2. R1 parallel R2 equals 3K multiplied by 6K divided by 9K equals 2K. Add R3, which is 2K. R Norton equals 2K plus 2K equals 4 kilo ohms. So R Norton equals 4 kilo ohms. Final circuit, 4 milliamp source pointing up, parallel with 4K resistor. Let's check. Remember R Thevenin was 4K, matches. Remember V Thevenin was 16V. Does I Norton times R Norton equal V Thevenin? 4 milliamps multiplied by 4 kiloohms equals 16 volts. It works beautifully. We found the exact same equivalent behavior using a completely different method. Let's bring it all home. To find I Norton, short the terminals, calculate the current through the wire. To find R Norton, kill sources, look into terminals. Norton vs Thevenin. Thevenin is voltage source plus series resistor, best for series circuits. Norton is current source plus parallel resistor, best for parallel circuits. You can switch between them using source transformation. V equals I asterisk R. You now have two powerful tools in your belt. Don't be afraid to use Norton's theorem. It's not the backup theorem, it's the current expert. Practice these steps. Short the output, find the current. It's that simple. Check the description for practice problems. Thanks for watching and keep analyzing.